Hey guys, welcome back in. Mr. Marone here. So we are in section 7.2, which is all about similarity transformations, where we're going to take that idea of a dilation and apply it using translations and rotations and reflections and all that good stuff. So in our case here, in all of these, we're going to be dilating around the origin. So we can take whatever the scale factor is and just multiply that with each coordinate point to get our new location with our dilations, which makes life a little bit easier for us. So in this first example here, they've given us a composition of transformations. Remember, you always do the right-hand one first. So we're going to dilate this first. So I've got the points listed there. And if I'm dilating first, I'm going to multiply each of those by 0.5, or I'm going to cut them all in half. So for my case, A is going to become 1, 2, and we're just going to follow that pattern as we work our way down. So right there, I've got 1, 2, I've got -1, 4, and I've got 0, 5. So there's my figure dilated by half. Now they want me to reflect over line M. And they said line M is the equation x equals -3, or this line right here. So I'm now going to take those points and reflect them across that line. And I'll change colors here so we have a different color. So this point here is 2 units away, so I'm going to go 2 units to the other side. This is 3 units away. And 1, 2, 3, 4 units away. 2, 3, 4 units away. So right there is going to be my final graph, and if we look closely at these points, you've got B prime, C prime, and A prime there. So this is A double prime, which is at -7, 2. You've got B double prime here, which is at -5, 4. And then you've got C double prime here, which is at -6, 5. So doing a dilation, you're going to have the dilation first in this case, and then your reflection. The process remains the same. It's just that we're now adding an extra one of being able to change the size of the figure, in addition to sliding it, rotating it, and reflecting it. There are 2 there for you guys to try. They're asking you to do this using the point 3,5. So you're only moving 1 point here. Go ahead and try that, and remember, we work right to left. Okay, welcome back in. So honestly speaking, I think it's easier to do these when you're just given the points and not the graph. That's why my first thing to do is to pull them out in our first example. So looking at this, if I take 3, 5 and I translate it 1 unit right and 2 units down, I have 4, 3, and then I multiply by that dilation factor, scale factor of 2, so it becomes 8, 6. And then in my second one, I took my point and rotated 90 degrees, which was taking our original and doing -yx, and then I multiplied by a factor of 3. So now you've got the flip side of it. They want to know, is there a composition of transformations that takes my original graph and turns it into this? So the first thing I'm going to do, if we're looking at it, it appears that it has rotated by some amount. What it looks like is 180 degrees. So I think we've got a rotation of 180 degrees around the origin. We can check that as we work through it. And then it looks like it got further away from the origin, which means it got bigger. And if we want to count, from X to Z is 2 units. From J to L is 4 units. That's 2, and this is 4. So it appears that it was a dilation of 2 in order to make this happen. And the only way to verify this is to try it. And I know that I'm making it seem very easy, and I'm almost cavalier in being able to solve it, but you're really just using what you've already learned. Knowing that in order for this figure to turn like it did, it's got to be a rotation. And then knowing that my original figure is smaller than my bigger figure tells me it's going to be a dilation larger. And so if we were to verify this just with point X is the point 2, 1. If we rotate that 180 degrees, that becomes -2, -1 right here. And then if I were to dilate that by a scale factor of 2, it becomes -4, -2, which is point J. So it allows me to verify it, and we could do that with z and with y too if we wanted to. We don't have to, though. If you'd like to try this on your own, you can. Looking at this here, they didn't give us a graph. They didn't give us any sort of coordinates, so you're really just going to have to describe it on your own. Go ahead and see if you can try to describe it. Which one comes first, which one comes second, and go from there. All right, welcome back in, guys. So as you can tell, I saw that my original figure was in black and my new figure was with the prime marks next to each coordinate point. So it's going to be a reflection across some sort of a horizontal line, and it's going to reflect up in order to get the points in the correct orientation. And then my original figure is larger than my new figure, so it will be a smaller dilation. It's by some some fraction or some decimal less than 1. So that's just a quick example there for you. So just to finish up here, the idea of similarity is it's a composition of transformations, including dilations, where the shape does not change, but the size does. And the difference in the size of the shape is that they're proportional. So the shape's not going to get bent out of proportion. It's going to save its proportions. It's just getting bigger or smaller. The angle measures, though, will remain the same. So as we do this, it will stay the same that way. One thing to note that they talk about here as we wrap up is that all circles are considered similar. No matter what kind of circle you have, whatever size radius it is, every circle will be similar. So bring any questions you may have into class tomorrow, and I will talk to you then. Have a great night, guys. Bye-bye.